The second type of interest point we will study are corners. So we will talk about corner detection. Now, while edges were prominent structures, they're kind of also everywhere, and maybe they're not as distinctive as we thought. So consider a pixel pattern within the blue patch here, and assume that in this image, inside this wedge, it's completely black, and outside it's completely white. Now, if I look at the pixel patterns here and study how they change as I shift this patch, I should get a good idea of what's really distinctive. So in the flat region, if I shift this pattern across the image, I see that the intensity patterns within this blue patch will not change. So it's actually, homogeneous areas are not distinctive at all. In the edge, if I move this pattern across the edge, then true, I will have a difference in intensity patterns. So edges actually might be quite distinctive if I look at across the edge. However, along the edge, if I move this patch, I see that the intensity pattern does not change. So it's not as distinctive as I thought. But the corners, now, if I move this pattern in any direction, I see that there will be a change. Actually, there's a significant change in all directions. So maybe actually corners are better distinctive areas in the image that I should be detecting. So let's think about this a little bit better. And we will actually derive how corners are distinctive, and that derivation will give us an idea of how we can detect them as well. So consider a patch here, and consider that we shift the patch in U and V direction. So U and V can be any direction. And we will study how the pixels within this W patch or window is changing. We will use sum of square differences, SSD, before and after the shift. And we'll compare the pixel intensity, the intensities of the pixels using SSD. So high change means that there's a distinct patch from its surrounding. Low change or low SSD will mean that patch is not distinct at all. This SSD difference, sum of square difference, is actually defined like this. So I really look at the intensities within the patch after making a U and V shift and before. I compute the differences between corresponding pixels and I simply square them and sum them within the window. Now looking at this is kind of difficult to basically play with it. So we will look at the first order Taylor expansion. So we will expand the shifted patch using this form here. So intensity image x plus u and y plus u can actually be approximated simply by the intensities x plus y and then the first order derivatives of the image in u and v direction. If the motion uv is small, then the higher order terms will die out and the first order approximation will actually be a good one to the actual intensities of the shifted patch. Now, if I plug this in the formula, I can actually write this in terms of the gradients of the image. So ix plus y plus the gradient of the image dot product with the u and v direction. Now, plugging this inside the formula here, I get this guy. Now, the SSD difference was given like this. Plugging it here and using the shorthand notation for the partial derivatives, I see that ix plus y plus the derivatives dot product with u minus ixy squared. So ixy's cancel out, and I'm only left with the square of this guy. Now, writing it explicitly, I will notice that actually this corresponds to uv times a matrix that's actually composed of squares of the first order derivatives and the products of the first order derivatives in the diagonals times again the uv. Now, as uv vector does not depend on x and y, nor it depends on the window, it can actually be taken out of the summation. So when I take it out, I see that it's uv times the sum of this matrix over the window, and then again uv, and the matrix here is actually what's called the structure tensor of the image. And I can simply write it as this guy here. So UV times H times UV. So it's the inner product of UV with respect to the structure tensor. Now this form approximates which directions approximates the change in the UV direction that I should see in the intensity patterns. Now looking at this, I can ask the question, so which direction of U and V will result in the largest and the smallest changes in E? So once again, writing the change here with the structure tensor here, I noticed that I actually know this form quite well. Indeed, it's the eigenvalues and the eigenvectors of H that are useful. So if I want to define shifts with the smallest and the largest changes in E, I should simply look at first x plus, the direction of the largest increase in E, is actually the eigenvector that corresponds to the largest eigenvalue. And the largest eigenvalue tells me the amount of increase in the direction of x plus. Similarly, the direction of smallest increase in E will correspond to the eigenvector, and the corresponding eigenvalue will give me the amount of increase in the direction of x minus. So by simply examining the eigenvalues and eigenvectors of the structure tensor, I get an idea of which directions leads to the largest change in intensity patterns and which direction leads to the smallest change in intensity patterns. Let's look at it in a very small example. So if I want now largest change in the EUV direction, or if I want basically the intensity patterns to change as much as possible in all directions, that means I have to make sure that even the smallest eigenvalue of the structure tensor should be large. And this is indeed the case if I look at an image like this, which is actually composed only of edges and corners. Now, at each point, I compute the structure tensor using the formula that I've shown before. And then I look at the eigenvalues of the structure tensor. I look at the largest eigenvalues, which, as you can see, is large in all the edges and the corners. And I look at the smallest eigenvalue, which notice something interesting, which is only large at exactly the corners. Well, it's natural because in the edges, along the edge, there is no change. So the smallest eigenvalue of the structure tensor should be 0. But in the corner, there's change everywhere. So the smallest eigenvalue is quite large. So zooming into it, I see that actually it's really taking this the orthogonal directions of the corner. So, okay, the smallest eigenvalue is actually quite nice. And I also see that the smallest eigenvalue is only very large at the corners, meaning that corners are really interesting points. They're distinctive. Indeed, corners are the most prominent examples of interest points. They can be well localized in different views of a scene. So a corner is a corner, even it's viewed in different angles, as long as it's visible. So that's quite nice. Actually, similar to corners, there's another concept that we'll see, but basically the same discussion applies, which are the blobs. So very similar to corners, a blob is a region with intensity changes in all directions. So they end up being very prominent examples of interest points as well. But we'll study that in a second. Okay, so we've seen that actually by looking at the smallest eigenvalue, I see that the smallest eigenvalue is very large in the corners. Now turning it around and asking the question, so how can I actually create an algorithm to detect corners? Well, I will use the same idea. And that will lead to me what's called the Herod's corner detector. The goal here is I want one approach that is able to detect and distinguish homogeneous areas, edges, and corners. And the key is the ideas that we use to analyze uniqueness of a patch will end up being the detection tool. So we will look at the structure tensor, and we will look at the eigenvalues of the structure tensor, and we will look at intensity variations in different directions. So for a homogeneous region, the intensity variations in all directions should be small. For an edge, the intensity changes only in one direction should be large, while the other one should be small. And for a corner, the intensity change should be large in all directions, meaning that the eigenvalues should reflect this. Very specifically, if I see two small eigenvalues of a structure tensor, that means I'm actually at a homogeneous area. if I see one large and one small eigenvalue, that means I'm on an edge. And if I see two large eigenvalues, that means that I'm at a corner. If I look at actually a plot of the first eigenvalue and the largest eigenvalue and the smallest eigenvalue, the different areas look something like this. Here, I will have homogeneous areas in an image, so small eigenvalues. Along each of the directions, I will have actually edges, and corners will lie somewhere here where both eigenvalues are large. So by looking at the eigenvalues, we actually get two different maps. Remember this here? We have two maps, the large eigenvalue and the small eigenvalue. Instead, we would like to combine the two maps and simply have a single detection result. So one score, what we can look at, and that will tell us whether I see a corner or not. That would be the corner detection. A simple way to do it would be simply by looking at the product of the eigenvalues, because if I have both eigenvalues large, then their product should be large as well. However, that doesn't work very well, because if I have a very prominent edge, that will also give me a large product, a large determinant. Okay, and a weak corner will give me a smaller product. So that doesn't really work. A refined strategy would actually look at the difference between the determinant, meaning the product of the eigenvalues, minus the trace of the method. So this is actually nicer, because now, first of all, I don't have to compute the eigenvalues. I can simply compute the determinant and the trace of the matrix. And second, if I look at the isolines for this score here, I get this guy. So it really is able to distinguish. You see different isolines of the score. It's able to really distinguish the edge regions from the corner regions and from the flat areas here. And if I look at the response of the Harris corner detector, meaning that determinant minus the trace square, the response really looks like at the corners the smallest eigenvalue. I see that the response in the squared image that we've seen before for the Harris corner detector is this guy, while the minimum eigenvalue was this guy. And notice that it only highlights the corner points. So that's quite nice. To compare this image, really, the original image was given here. The smallest eigenvalue was reflecting or was highlighting the corners, and the Harris corner detector is also similarly highlights the corners nicely. Good. So we actually now have a method that really uses the analysis tools on the eigenvalues that we can use to detect corners in an image. And if we apply it, we see something like this. So this image, we see a lot of corners are present, and the Harris corner detector really highlights most of these corners quite nicely. And notice that it doesn't highlight edges, which is exactly what we wanted. So Harris corner detector is able to highlight the corners that we can actually use as point of interest. So based on this topic, we can ask a very similar question saying that, so are corners really stable under different viewpoints and illumination changes? So can we really use them as points of interest reliably? And that we can actually visually test. Let's assume that I have this object in two different viewpoints and two different illuminations. Now I can apply the Harris corner detector, and this will basically be all the responses. Okay, red means high, blue means low response. And then I can threshold this, and I will get all these points. So I thresholded to extract the largest Harris corner detector responses in the image. Now, this doesn't mean much, although you can actually kind of see the profile of the object in these points. Let's put those points back onto the images. And I see something very nice. I see that actually structures, for example, the horns here, are detected on both of the viewpoints and the illumination reliably. The same thing applies for the nose. The same thing applies for the tail. The same thing applies for the foot. So that's quite nice, actually. So it is indeed that corners detected through Harris corner detector are reliable interest points that are stable across different viewpoints when illumination changes. But of course, you have to note that some of these, if they're not visible in the image, for example, the nose here, which is not visible in this image, will not be detected. But that's fine. because our strategy for extracting features was to extract features from all these local areas. Okay, and we'll get to that in a second as well.